The previous video was on the meaning of B and beta. Now we're going to shift to some other letters, mostly just R. And what is R? So specifically, we want to know there's all this output that we get here. And let me just show you what the output looks like from. So this is from our model LM4.3, which is our model that has our dependent variable and two predictors. So if we look, we've already gone over the coefficients right here. So we've done B's, and that's this first column under estimate. And the B's in this case, these are B's. I haven't standardized anything. And now what we're going to do is we're going to shift to this bottom row here. And specifically, we're going to look at R squared, adjusted R squared, and what R means. So to begin with, I want to talk about R. So what is R? And R is simply the multiple correlation. So similar to little r, where it's a correlation between two variables, well, big R, capital R, is the correlation between the y observed and y expected. So I'm just going to put a note here. The correlation between observed and expected. And that correlation gives us R. So if I do a summary of our previous model, you'll see I get all of this, but I don't really have multiple. I don't have just multiple R. And the reason why we don't have multiple R is similar to little r, or Pearson product moment correlation. They're difficult to interpret alone. Now, because it's part of our lexicon in social and behavioral sciences, we look at little r and we say, oh yeah, that's big or that's small. And it's nice to have it in absolute value so that we can get both the magnitude of the effect or the relationship as well as the direction. But generally, we don't use capital R or multiple R. Instead, what's reported is R squared, and that's what you see in this line here. You see multiple R squared and adjusted R squared. So if big R is the correlation between the observed criterion or dependent variable and the expected, which is what we get from our regression model, R squared is simply the squared version of that. So if I square that, I get 0.317. And sure enough, that's precisely what we see right here. Okay? That R squared is also a ratio of variances. So let me just show you here that I have a ratio of variance specified in this model where I have the variance of the predicted value divided by the variance of the observed value. Now, you notice that the values that I've calculated are identical. So one of them is a correlation squared, and the other is the ratio of variances. So remember, a lot of you have had me in courses before, and I said a lot of what's in statistics are nothing more than ratios of variances, and that variance is really an essential part of all of statistics. Now, to provide a little bit of logic to this, I want to go back to classical test theory so that you can see this, so we're tying in a lot of these common themes. So if you recall from classical test theory, we have observed score variance is equal to true score variance plus error. Now, the objective that we want to do in measurement is to reduce error. So we want to be able to reproduce true score variance. And so therefore, we calculate the reliability as a ratio of true score variance to observed score variance, which is nothing more than just this part, true score over true score plus error. Now, why is that? Well, observed score variance has both true score variance and error variance. And as we decrease error variance here, what we ought to be doing is reproducing true score variance without having to inflate it, because we know that observed score variance is bigger than true score variance. Okay? Now, by decreasing error variance, what we're doing is we're getting the variance of our observed scores to be similar to the variance of our true score. Now, the same logic holds for R squared. We expect to reproduce the observed score variance from an expected score. So what we have is we have observed score and expected y. So we have y and y hat. And the regression line that we often fit, or the simple one, is y equals y hat plus error, where y hat is our deterministic model. That's the one with all the b's in it and the a and all of that. So by reducing our error variance, we increase y hat variance to match y. Or really what we're doing is we're not increasing y hat variance, but what we're doing is we're reducing the variance in our error. And ideally what we would like is to be able to replicate the observed score variance, and so therefore the r squared is exactly the opposite ratio of what we had before, but it's in the same line. See, here we have y observed out here, and what we're trying to do is we're actually trying to replicate the observed score variance. Remember, here we're trying to replicate true score variance, but the true score really comes in regression as the observed scores, our criterion, and our observed scores are always y. So remember that the ratio of variances is what we are interested in actually reducing, is going to be a component here in the bottom, because remember that the variance of y is going to be the variance of y hat plus the variance of the error, because that's in this equation here, right? And so therefore in our numerator we have the variance of y hat over the variance of y, and that gives us our r squared. That tells us how much variance, what proportion of variance of our observed variable we are modeling with our expected value equation. Okay, now all that being said, what we're doing with that r and r squared is just telling us, is giving us a reflection of the amount of variance that is explained in our model. The problem with just using r is that r is also a summation of all of the betas. So if we squared all of our betas and we added them up, what we would get is we would get a function, a linear aggregate function of all of these unit weighted predictions with each one of our predictors. Now what happens when we have small sample sizes? Well, imagine that you have a predictor that has really zero predictive validity for our dependent variable. If we have something that has zero predictive validity, then what will happen is that variable may or may not be actually zero with a small sample size. It may be the beta may be slightly negative, it may be slightly positive, but it doesn't matter the direction, because when you square it, it becomes positive. So we're always adding up variance. We're always adding up variance accounted for in our r squared. But in the population, there may actually be trivial or zero betas that get overestimated in the beta squared. So there is an adjustment that we can do, and that adjustment is reflected here in this adjusted r squared. And the adjusted r squared is a function that is essentially a penalizing function, and that penalizing function takes our r squared that we computed and it adjusts for that r squared according to the sample size and according to the number of predictors. And you can see here I have a typo in my equation, and I'll just have to fix this. Here's the problem with PEMDAS. All right, let's see how we did. The great thing about calculating these things is if you get a value that doesn't make any sense, you just go back to your equation and fix the parentheses. Okay, so adjusted r squared is nothing more than adjusting the r squared to punish you for having too many predictors or small sample size. Now in this case, the number of predictors I have is 2, so that's why I've highlighted it here. And the sample size is just the length of my y variable. It's an easy way to find it. Now this 2 will change given the complexity of the model. So the more predictors I have in the model, k increases. Now what happens when k increases? As you have more predictors in your model, because it's in the denominator here, and you can refer to page, I don't know, let's see, page 84 in Cohen and Cohen, West and Aiken, you'll see that they have the equation for shrunken r squared or adjusted r squared. Now this adjustment procedure penalizes you for small sample sizes and lots of predictors. And why is that? Well, the smaller the sample size, the more likely we are to have trivial correlations or trivial betas, squared betas, that contribute to r squared. So what it does is, as you include more predictors, the equation penalizes or punishes you for having more predictors by just subtracting out the potential for having spurious beta squares in there that artificially inflate your r squared. Second, what it does is it punishes you for small sample sizes. And the reason for that, again, is small sample sizes produce correlations that may have a great deal of standard error, so there's not a lot of precision to those estimates. As the sample size increases to, say, 100 or 200, that r squared and adjusted r squared eventually start, they are asymptotically similar. Maybe not 100, but 200, certainly 400, really doesn't matter the number of predictors. And so what you'll find is that these values converge with fairly large numbers. And you can see for my 2 predictor model with 100 observations, I believe I have 100 observations, that you'll see that the multiple r squared and the adjusted r squared, this one is 0.32 and this one is 0.30. They're pretty similar. As we have larger sample sizes, the larger sample sizes pretty much take out any influence that the number of predictors will have on our model, and so therefore we will have a convergence between r squared and adjusted r squared. So r, remember, is the multiple r, and that's the correlation between the observed and expected y, and that multiple r, when we square it, gives us the proportion of the variance that's explained by our model of the observed y variable. Okay, remember that all of this is a ratio of variances, and then shrunken r squared or adjusted r squared is a penalizing function. It imposes a penalty for large samples, or for small sample sizes, small sample sizes and really complex models. So adjusted r squared is nothing more than a parsimony adjustment. We want fewer predictors, and we want larger sample sizes to produce a shrunken r squared or adjusted r squared that is essentially identical to r squared. Okay, in our next video, we're going to talk about significance tests for r and b and beta. So stay tuned for that.